Welcome to a brief presentation of the Newtons4th PPA5530 Precision Power Analyzer. Here we will demonstrate a range of power measurements on a variable speed inverter drive and illustrate solutions to some typical problems associated with this application. First, we switch on the instrument using the power button. The instrument will go through a startup routine, then automatically select appropriate measurement ranges, synchronize with the waveform to which the instrument is connected, and present a range of key power measurement functions. Here we have the sum screen, showing the total and fundamental values with total power, frequency, mechanical power, and electrical to mechanical efficiency, highlighted via a zoom function. While we're looking at the screen, we can illustrate use of the zoom function to increase or reduce the size of chosen measurement functions. Selection of the zoom functions is achieved by pressing the zoom minus button to minimize the character size, and then pressing the zoom plus button once will add boxes around the zoom items presently selected. The cursor keys can be used to choose any four functions we wish to highlight, for example watts, volts, amps and frequency, which are typical selections when making power measurements. Once zoom functions have been selected, we can then go to any phase that we want to monitor by pressing the next button. Pressing the next key again takes us from the sum values to all three phases displayed simultaneously. Here we can see the total power, volts, current and frequency, plus all of the main power parameters, including at the bottom of the display phase-to-phase voltage from direct star to delta conversion. PWM applications involve complex waveforms, and this can be seen if we select the scope mode. Here we can see the voltage waveforms for all three phases of the drive that we have connected. By pressing next, we see the current waveform with a sinusoidal fundamental component and a large amount of noise. If we move to a single phase, we can see one phase with volts and current together. The switching frequency and its associated harmonic components make detection of the correct fundamental frequency very difficult for many power analyzers. In order to solve this problem, it is quite common for measurement instruments to apply a filter that will reduce the carrier and noise. Filtering from around 30 kHz is commonly used for this purpose. So, by using the bandwidth function, we can apply a 30 kHz filter. We can see that the filter removes much of the noise, resulting in a clean sine wave current, which is going to be easy for frequency detection. However, the impact of this filtering on the voltage waveform is also significant, and we would like to illustrate this. First, we will return to a full 2 MHz bandwidth, using the bandwidth function again so that there is no filtering. We can clearly see high frequency noise visible on the current waveform again. Using the scope mode time-based control, we can zoom in to the voltage waveform in order to look at the PWM switching. If we now select hold in the scope mode, we can pause the display and see that there are fast rising and falling edges, accurately representing the PWM signal. We can now change the bandwidth back to 30 kHz and pause the display again. It can easily be seen that the waveform rise time has been significantly reduced by filtering. This will inevitably influence the accuracy of total power measurement. We can illustrate this in more detail by looking at the voltage and the power screen while we are still in low bandwidth. Here you can see that while we are still in low bandwidth, we have a nominal 120 volts phase to neutral. If we now reselect wide bandwidth, giving DC to 2 MHz, the voltage is increased to 131 volts. So, we have approximately 10 volts difference due only to frequency components above 30 kHz. Since switching frequency components are present in both the voltage and current signals, it is clear that filtering will reduce the accuracy of wideband measurements. Staying in wideband, we can now illustrate the ability of the PPA to synchronize with the fundamental frequency with no problem, while maintaining the high frequency noise we have seen with an unfiltered input. We do this simply by changing the drive frequency, which you can now see increasing as the drive speed is changed. Now we start a data log, which enables any selected zoom functions to be stored directly to internal memory or to an external USB. Here we can see all of the 4 measurements that we selected with the zoom function being logged directly into the instrument at the selected data log update speed. If we go to the graph, we can see the change as I reduce the frequency and then increase the frequency again. And we have real-time monitoring with no break in measurement. If we now stop the data log, we can use a cursor to select any point in our measurement period, and by pressing table, we can look at that point with direct measurement or move back to real time. Thank you for watching. We hope you found this presentation useful.